Good morning, sir.
Yeah. So hope all of you understood the basics of projectile motion that we discussed in the last lecture, and all the equations of motion, especially velocity and position as a function of time, both in component form as well as vector form. And from that, the derivation of the standard quantities like maximum height, horizontal range, etc. And finally, the part about the equation of trajectory. Okay, so we'll discuss few typical types of questions today, especially involving equation of trajectory. And then we'll start looking at the variations of the standard projectile motion, like projectile motion from a heighted position or projectile motion on an inclined plane, etc. So let's begin. Okay, so I'm just reiterating on the standard formulae and the equations that we derived for projectile motion once. Couple of special points related to them that we'll discuss. We already discussed about the symmetry in the ascent part of the motion and the descent part of the motion, both in terms of geometrically how the shape of the path looks, as well as in terms of the values. So this is the trajectory, the parabolic path. Seen that this is the projection at t equal to 0. Then specifically it reaches the maximum height at half the total time of flight, with at the instant when it reaches the maximum height, the velocity is horizontal vector, which is u cos theta, and the time is exactly half the total time of flight. And of course, the impact happens with a symmetrical angle, okay, at the same speed at the time of flight, capital T. And we had seen this aspect of symmetry that we discussed about, that if at these two instants of time in between, the heights are the same. So whatever this coordinate y1 is, y2 is the same as y1. Okay. That is, of course, taking a standard system of reference, that this is x-axis and this is the y-axis. This point of projection is the origin. Okay. So this coordinate is x1, this coordinate is x2. This velocity is v1, this time is t1. Then this velocity is v2, this time is t2. So we had seen that if y1 is equal to y2 at t equal to t1 and t2, then it automatically implies that t2 is equal to capital T minus t1, or t1 plus t2 is the total time of flight. Okay. And x2 is equal to range minus x1, or x1 plus x2 is equal to the range. Where of course, when it reaches this position, you can see that the x coordinate is the range and the y coordinate is 0. So that was about the symmetry in that ascent and descent part of the motion. Okay. And of course, we had these standard equations that in general, as a function of time, coordinates and velocity we know how to write. Okay. And also one more thing over here, that v2 is equal to v1 in magnitude, or if v1 is equal to u cos theta as a x component plus some vy, then v2 will be u cos theta I cap minus of that same amount of y projection, but along the negative axis. So this is the symmetry part. symmetry of ascent and descent. So this is useful in certain types of problems. Okay, of course, before this, the main thing that is like the universal method of solving everything is that the four equations: x as a function of time, y coordinate as a function of time. So these equations all should be very natural for you. You should not have to think twice about how to write them. Then the problem solving will come in flow without any stick ups in between and all that. Okay. So these are the fundamental four equations, you can say, from which everything is derived. And this gives us the standard formula that range is u square sine 2 theta by g. But I told you the better way to remember the concept of range is that it is ux multiplied by time of flight. Time of flight is 2u sine theta by g. But conceptually, the way to remember it is that it is 2uy divided by g. Okay, and maximum height is u square sine square theta divided by 2g. Conceptually, the way to remember it is that it is uy square by 2g. Okay. And then also from this set of equations, you have the equation of trajectory. And that also we saw there are two ways of writing it. One is like what you get directly when you eliminate time. You get this, what looks like a very complicated expression. But when you just manipulate this a little bit further, then you get something that is very logically obvious in terms of the parabolic graph. Why it is obvious also we had discussed that it's a downward pointing parabola which has roots 0 and capital R. And also if you draw a tangent at the point of projection, the slope of the tangent should be tan theta. That is the direction of the instantaneous velocity. So that's why. Okay. So just make a quick run through of these formulae like a chart. Okay, it's like not only you should know all these formulae and you should have this chart yourself, but you should be able to construct this chart within a minute if required, without any reference to your earlier notes and all that. That's the way to perfect projectile motion. You can actually write down these equations within a couple of minutes without thinking too much about it. If you have that kind of flow in your understanding of derivations and theory, you will see your problem solving will be at least 25-30% faster. Okay. So just go through this once. We will continue.
Done, sir.
Oh, very good. I just have a couple of questions. Equation of h should be equal to u square sine square theta minus half. नहीं बेटा अभिनव, I'm just going through your question. You're talking about the maximum height, no? So the value of the maximum height is independent of time, no? It depends on u and theta. So
Yes,
u
sir.
square, got it, no? Understood?
Yes, sir.
Point is clear, no? Okay. So basically, you just put the value of time as u cos theta, sorry, u sine theta divided by g in that second equation, that equation of y as a function of time. Or there's another thing that you can do for finding the maximum height. If you look at the components of velocity, there is also a relation like this, that vy square at any time is equal to u square sine square theta. V square is equal to u square plus 2as, that equation. So minus 2gy. So this is also an interesting equation that you can use. Okay. So in this, you can see the relationship is between the instantaneous value of y component of velocity and the instantaneous y coordinate of the projectile. So now the thing is, see what happens when it reaches the maximum height. The y coordinate is h, but vy should be 0. So we can put in this equation that I've just written, you can put vy on the left hand side as 0, and the value of y becomes h. So that's an easy way to remember that why its maximum height is uy square by 2g. Uy is of course u sine theta. Okay, now so hope these equations are all clear. Now just a couple of more additional points to discuss about the application of these things before we move on to a very typical type of numerical problems. So one is the concept of maximum range for a given speed of projection. So you can see that since the range as a formula comes out to be u square sine 2 theta divided by g. As a concept, of course, it is equal to ux multiplied by time of flight, which is ux into 2uy divided by g. So what we understand that for a given speed of projection, given value of u, that is, if we can throw a projectile at some given maximum speed of, let's say, 20 meters per second or 40 meters per second, that is a limitation, that we can throw it only at that much speed. But we can throw it at any angle of choice. So we can throw it, for example, horizontally at 0 degrees or completely vertically at 90 degrees, or any angle in between 0 and 90. Then what angle we should select so that we will achieve the maximum range? So that is called the maximum range theorem or the maximum range concept. So for a given value of u, okay, the range can be maximized by taking the value of, as you can understand, by taking the value of theta as how much? 45
45.
degrees, no? Because, yeah, okay. So this happens because range will be maximum when, for a given value of u, when this quantity sine 2 theta, we are maximizing this. So that will become u square by g for 2 theta equal to 90 degrees. Sine 2 theta is equal to 1, which is its maximum. Or theta is equal to 30 degrees. Sorry, theta is equal to 45 degrees. So, for example, if we have a cannon or a bowling machine or something like that, you can say, which keeps projecting objects at a given speed, given fixed speed, then to maximize the range, we have to point it at 45-degree angle. Okay, and so this is called the maximum range theorem. And the value of the maximum range for a given projection speed is u square by h. Okay, so while this might seem odd, I mean, mathematically it's very clear, but physically it might seem a little odd. But you can understand why that is happening. Okay, it's happening because range is equal to ux into time of flight, or ux into 2uy by g. So the product of these two things is maximum. Okay, because one depends on cos theta, one depends on sin theta. So since ux is proportional to cos theta, uy is proportional to sin theta. So therefore, the range is proportional to the product of cos theta into sin theta. So the range is maximum for that situation. So product of sin and cos is proportional to sin to theta like that. So this is one important special aspect of projectile motion to keep in mind. So a simple direct question would be, suppose you can throw a projectile at a speed of 20 meters per second. What is the maximum range you can achieve with it? The answer is simply 20 square divided by g. If you take g as 10, it's 40 meters. So no matter what angle you project it at, if your projection speed cannot be faster than 20 meters per second, then you cannot throw it further than 40 meters for g equal to 10. Now, another important aspect to understand about projectiles is that for any theta angle of projection not equal to 45 degrees, if theta is taken to be 90 minus theta instead, then the range is the same. So I'll just explain this with an example. So what this is trying to say here is that if we are projecting at a given speed of projection and given angle of projection, and that angle is not equal to 45 degrees, okay, and we achieve a certain range. So let's say we are projecting here at some speed u, at some angle alpha, let's say, okay, and alpha is, let's say, less than 45 degrees. So it's going in this kind of a path. It's achieving a certain amount of range, and it's of course achieving a certain amount of height and a certain time of flight. Now, instead of this, if we were to project it at an angle beta like this, but at the same speed of projection, and beta is 90 degrees minus alpha, then what would happen is we would observe that the projectile would go in this kind of path, would go to a greater maximum height. It would therefore take more time to reach the ground, but it would have the same range. Let's understand this with an example. So suppose our speed of projection is 50 meters per second, and alpha is, let's say, 37 degrees, and g is 10 meters per second square. So we can see that the range will become, ux will be in this case 40, and time of flight will be 6. So range will be 240 meters. Maximum height you can see is going up to going with a vertical speed of 30. So I mean initial uy of 30. So 30 into 30 divided by 20. So that's how much? 45 meters. Okay. And the time of flight is 6 seconds. But for the same speed of projection, if we change the angle of projection, theta is equal to 90 minus alpha, or in this case 50 degrees, 53 degrees, then you'll see that the range remains equal as 240 meters, even though the height will change. Okay. because now your vertical uy has become 40 instead of 30. So it's 40 square by 20. So it will go up to a height of 80 meters. And the time of flight will similarly change to 8 seconds. But the range will be the same. That r prime is equal to r because beta was equal to 90 minus. So other than an angle of projection of 45 degrees, you can achieve the same range for a given projectile by changing the angle to 90 minus the angle of projection. Even though the trajectory will change, the height, the time will change, it will land at the same position or at the same range at least.
So could you please scroll up to the part above this?
Okay. Above this was the maximum range theorem. Okay. Hope the concept is
Yes.
clear for it. Yeah. The concept is clear now for maximum range theorem.
Yes, sir.
Yeah. Okay, this is done, better.
Yes, sir. Done.
Okay. Okay, now let's come to some typical type of examples, especially examples where we'll see how we can use the concept of equation of trajectory quite effectively. So as I told you, if anything requires us to solve something geometrically, like position, displacement, etc., rather than in terms of time, that at what time it's reaching this place, at what time the velocity is becoming this much, etc., those kind of things, then using equation of trajectory becomes like a priority option. Okay? Whereas if something is time based, then we cannot use equation of trajectory that successfully. We have to use the time-based equations of x, y, vx, vy, etc. Those kind of things. Okay. So suppose something like this is happening. So suppose this distance is given to us, and u and theta are given to us, and we have to calculate this height at which it hits. Okay, something like this we have to calculate. So given that u is, let us say, 50 meters per second, and the angle of projection is 45 degrees. So if the wall is at a distance ahead of say 200 meters, then we have to find this capital D, which is like the height at which it hits the wall. So this is a typical example where if we use equation of trajectory, then it's going to be very effective. Okay, so let's understand how it's going to be very effective. So this is a calculation to do with the geometry of the trajectory. So will be easier by using equation of trajectory. Let's understand how. So to set up the equation of trajectory, we have to, of course, set up the problem in terms of the standard reference frame. So I'll bring you back to the data of the question and all that. First, let's understand what I'm trying to say here in terms of the solution. So we will use our standard method of selecting a reference frame, and that is that we will take this as our y-axis and this as our x-axis. So the moment you do this, now you see it becomes a problem of geometry. This is a parabolic curve whose equation we know. Okay, and in this particular scheme of things, the wall is actually a vertical line. Okay. And wherever it hits the wall, let's say the coordinates are some x prime and y prime. So that point P is the point of intersection of the two things. So it's a geometry problem. Okay. We have reduced it to like a coordinate geometry problem of the line, that is the wall, and the parabola, that is the trajectory. Okay. So now, given the values and all, we know that the equation of trajectory, the parabolic curve, was given this by this formula: y is x tan theta into what would have been 1 minus x divided by r. Because it's not completing the this thing. Okay. So here tan theta is tan 45, which is 1, and r is u square sine 2 theta divided by g, which is 50 square into 1 divided by 10. So you can see it is 250 meters. So that is my, so the parabolic curve is x into 1 minus x by 250. And the wall is the line x equal to t, or x equal to, what was it, 200 meters, I think, right? So now the point P is the intersection of 1 and 2. Okay. So just substitute. Okay. So y coordinate should be equal to x prime minus 1 upon x prime upon 250, and x prime is equal to 200. Substitute this here. It's 200 to 1 minus 200 by 250, and that is nothing but our capital D. Capital D, that distance is only the y coordinate, so you can see it is 200 into 1 minus 4 by 5, right? It is 1/5 of 200. It is 40 meters. So it will hit the wall at a height of 40 meters. Now, if you try this problem by using the fundamental four equations that we discussed, that is x, y, and bx and by as functions of time, those kind of equations, you will see it is far more lengthy. The process is the same, okay, and it's not that it's difficult. You'll be able to solve it without mathematical difficulty as such, okay, but it's just going to be that much more tedious because you'll have to find the time at which it hits the wall and substitute that value of time for y as a function of time, and from that you will get that y prime coordinate or capital D. Whereas with equation of trajectory, this becomes a one-step process. Okay. So just make a note of the data of the question and the method of solution as well as the value, so that when you are revising this later today, you can just numerically do this problem yourself once. You can also try this problem by the fundamental method without using equation of trajectory. I'll give you a hint below how to do that also, okay? But you'll see that this is the preferred method because it is a geometrical problem.
So can you scroll down a bit?
Yeah.
Sir,
Yes.
I didn't understand what geometry of the motion means.
The geometry means basically the shape of the path, expressed in terms of coordinate geometry. It's a parabolic path. The wall also is, so it's basically to do with position and the shape of the path. It's not to do with time. So therefore, we are saying that it's a problem that has to do with the geometry of the motion. That is, what is the shape of the path, what is the curve along which it's moving, and therefore, at which point on the wall it is hitting. So it's a geometry issue. No?
Okay, so we're not using time, and had we used time, we wouldn't have been able to use the equation of trajectory.
Exactly. Now, suppose the question had asked instead of this, it had asked that at what time it's going to hit the wall. Okay, then that's a time-based question. It's not a geometry-based question. This is asking at what height
Okay.
it hits the wall. So that's the
Right.
difference between a.
Okay. Okay. Sir.
Sir, if the object is a ball, sir, rubber ball maybe, then sir, it strikes the wall and elastically collides. Then on return, it will retrace the same path, right?
Yeah, like then we have to use the concept of elastic collision, and we will see later in a different chapter called collisions or center of mass concept actually. That if it is what is called a elastic collision, that means there is no loss of kinetic energy during the collision. Then the impact looks basically what is like a mirror image reflection. So the velocity before impact and the velocity after impact will be like the angle of incidence is equal to the angle of reflection, and there is no loss of kinetic energy. So the speed immediately after the collision is equal to the speed before the collision. So then what will happen is that the way it falls from the point P after impact will be like an exact mirror image of how it would have gone on if there had not been any wall. You understanding my point? No?
So,
So if the
sir,
wall had not been there, it would have gone further by a distance of how much? 50 meters, because the range is 250 meters.
yes, sir.
So if the impact with the wall is perfectly elastic, then when it rebounds from the wall, it will come back 50 meters.
Acha.
So where it
Sir,
will land on
the
the
small
ground,
curve.
it will be like a, just continue the parabola as if the wall is not there, and then fold the part which is beyond the wall like a mirror image on this side of the
Yes, sir, I
wall.
got it.
Right? But that thing is something we will look at in detail in collisions chapter. And not only that, we'll also see if the collision is not perfectly elastic, then what can happen? Because then the rebound will not be like a perfect mirror image. There will be some loss of kinetic energy. So it will not come back the same distance of 50 meters. It will come back a lesser distance.
Yes, sir.
Done, sir.
Okay. Okay. Okay, so this is clear. Now, just as an example, I'll show you what we would have done in this question had we not used equation of trajectory. By this simple method, by fundamental method, we would have solved this like this. We would have solved like this, that the motion started at t equal to 0 with u and theta. So what we would have done is when it hits the wall, say this is the wall, so it hits at the point P. Okay. We would have solved for time first. What is the time when it hits the wall? And for that, we would have required this value of t. So we have x is equal to u cos theta t. So in this case, x would have become, it was what? U was 50 meters per second and theta was 45 degrees. So x would have been 25 root 2 at t. And y is a function of time would have been u sine theta t minus half gt square. G we are taking as 10. So y as a function of time would have been 25 root 2 t minus 5 t square. Okay. So therefore, let's say this time is t prime. At t is equal to t prime, x is equal to x prime, which is that distance d. So that is x should be 200 meters. And y is equal to y prime, which is capital D. And that is what we want to find out. So from equation 1, we would have found out the time. 25 root 2 into t prime is equal to d, which is 200 meters. So this time would have been 200 divided by 25 root 2. So that is how much? 8 by root 2. So that is 4 root 2 seconds. Right. My calculation is correct? Yeah. And from equation 2, d is equal to 25 root 2 t prime minus 5 t prime square. So 25 root 2 into 4 root 2. So it's not that it's like something very difficult to calculate, it's just it's tedious. So let's see. So 25 fours are 100 into 2, so 200 minus 5 into 16 into 2, no? So 5 into 32. So that's how much? 160. So you can see it's 140, it's 40 meters. So the height at which it's hitting the wall would be 40 meters. Yes. Okay. So this is okay, but it's like much more indirect, okay, because we are first solving the time and then substituting the time in the second equation. Whereas that was direct because it's giving you a relation between x and y directly. Okay. So this is still a relatively direct and simple type of question. Okay. But we will see other types of questions where things can sometimes become a little more tricky. Okay, so this is done, I hope. Now let's move on to slightly more tricky type of question. So next example, we have a projectile that is given to us in terms of very indirect information. So what is given to us? It's like the range is given to us as 480 meters. The maximum height is given to us as 160 meters. Now, something very interesting. It's given to us that there are two like walls which the projectile just about clears. So these walls are of the same height of, let's say, 100 meters each. And the gap between them is some small d. And the point from which we are projecting is some capital D. So given that the projectile has this information, okay, given u and theta are such that the range r is equal to 480 meters and the maximum height is equal to 160 meters. G is equal to 10 meters per second square. And two walls, say A and B, are just about cleared. Just cleared by. That means the projectile is almost hitting the top of the walls, but just about clearing them. Then find capital D, what is the distance from the first wall at which the projectile should be fired, and small d, the gap between the two walls. So just try out this question. We'll discuss in a moment. So it's not that it's a very difficult question, but it's a slightly more sort of advanced sort of application of projectile motion concepts. And the hint to you is, again, you can see it's a purely geometrical problem. We are not asking anything which is time based. So the go-to method, the first method you should think of over here should be the equation of trajectory. If for some reason it doesn't work, you always have the fundamental equations as the backup. But you should start out by thinking of how I can use equation of trajectory. Okay, so if anybody's got the answer, please send to me. Okay, I'll give you one more hint also. Use the symmetry of ascent and descent. If you go back to the thing we discussed in the beginning of the lecture today, that symmetry, remember, there was a relationship between not only T1 and T2 at two symmetrical times when the y coordinate is the same, but also the relation between x1 and x2. Okay, so I will just check your answer first of all. So, see, the way I would approach the problem is that I can first determine the equation of trajectory. The parabola. Okay. Of course, taking this as our origin and y-axis and x-axis and all that. Equation of trajectory. And this we can see R directly is 480 meters. That's given. Okay. And we can also see that H is equal to 160 meters. Now H is basically what? H is equal to the value of Y at X equal to R by 2. Because you can see that the maximum height position is always where X is half the range and Y is maximum height. And this position is where X is R, Y is 0. So you can substitute this in equation 1. This equation 1 or equation of trajectory. You can substitute this in this, okay? So 160 should be equal to the X, Y coordinate when X is Y is equal to 160 when X is equal to 240 meters, okay? So it should be 240 into tan theta into 1 minus 240 divided by 480. So you have that relation which we had anyway seen between maximum height and range. So we have tan theta as 160 divided by 120 or 4 by 3, which means basically theta is 53 degrees. Okay. So going back to that, therefore, equation 1, it becomes y is equal to 4 by 3x into 1 minus x by 240. Now this is one. Okay. Now going back to the geometry, so this is the equation of trajectory. That's equation 1 we have got numerically completely, the relation between x and y. Now you can see that if this point is P1, where it just misses this, and this point is P2, there's a special relationship between these 2 points. And that special relationship is that y1 is equal to y2 is equal to 100 meters. Okay. Therefore, x1 plus x2 should be equal to r, which should be 480 meters. And x1 only is d. Okay. And x2 is capital D plus small d. So from that only we'll get these values. Okay. So it's pretty simple now, as you can see. So I'm just minimizing this a little.
Or
And
sir, we
see
can
if
just find sine theta, no, and we can substitute in any equation.
Sine theta is in, from the
Tan
equation
theta.
for maximum height. Yeah, you can do that also. Yes, you can work with those fundamental equations also. Sine theta, cos theta. So basically what you can understand here is that in my equation of trajectory, now equation 1 has become this. If you substitute the y coordinate as the height of these two walls, 100 meters. So because it's a quadratic equation, so substituting the value of y as one quantity, 100 meters, will give you two roots for x. And they are nothing but x1 and x2, where x1 is the smaller one, and that is nothing but the distance capital D that we're looking for, and x2 will naturally become capital D plus small d. So from that we'll just find the value of small d. Okay. So what I want you to pay attention to in this type of solution is like the concepts that we had learned about quadratic graphs, root of quadratic graph, the symmetry of it, the vertex point symmetry with respect to the two roots. So if you relate those graph-based properties that we had learned over there with the solution of this type of problem using equation of trajectory, then you have a much more effective method of solving these problems rather than somebody who's just using the fundamentals, which is x and y as function of time. For that kind of solution, it will become very lengthy and complicated. Whereas using these tricks that we've discussed now, it will become a very focused and sharp method of solving such problems. And this is the type of thing that you require for JEE Advanced. JEE Mains, you can still mostly concentrate on solving things by the fundamental equations or even using the direct formulae. Okay. But for JEE Advanced, you will have questions where little bit of these kind of tricks will come in very handy. Okay.
So in equation 1, why is it 1 minus x by 240?
No, so what we have done now, we have substituted the value of this point, the maximum height point.
Yes,
See?
sir. So from that equation, we got tan theta 4 by 3. But then y is equal to 4.
Oh, sorry. Yeah, in the end, it is 480. My mistake. Yeah.
Yes.
Correct. This should be corrected to 480. Yeah. This one, you're saying the final equation. Yeah, this value should be 480. That's correct.
Sir, so what's the answer that's coming?
I'll just have to check, but just give me a second. Okay. So this is 480. Now in this, what we will do is we'll substitute this data. Okay. So for the point P1, we can see we'll substitute P1 and P2 actually. We'll substitute y equal to how much? 100. So the values of x that we will get, x will be, those roots will be x1 and x2. That's what we have to solve. Okay. So is that 100 is equal to 4 by 3x minus, this will become how much? 4 by 3 into 1 by 480. No? So x square by 360 is correct. Okay, so let's see my quadratic equation. It's x square minus, if I take 360, so 120 into, so 480 x plus 360 into 100 now is equal to 0. This is my equation. So x will be equal to 480 plus minus 480 square minus 4 into 360 into 100 divided by 2. So what we can do here is we can take, obviously 10 we will take outside, and something else also we can take outside, because this term is 48 square. Anyway, so let's start with this by taking 10 outside. So what we're left with is 48 square minus 360 into 4 now.
Yes, sir.
So that I can write as 12 into 12.
So the 6 also you can take outside later, right?
Yes. That's what I'm saying. So we can take actually 12 outside. So this will become 240 plus minus 5 into 12, and this will become 48 is 12 into 4, so 16 minus 1. Let's check, is it correct what I've done?
Yes, sir.
So plus minus 60 root 15. Now root 15 is something you can like very easily solve numerically also, but before that, so what we are seeing that x is this, that means x1, which was our capital D, is the smaller root of the two. So it is 240 minus 60 root 15. And we'll do an approximate calculation of this in meters also.
93.
So that is the distance from the front of the first wall where you are hitting it. Okay. And your x2, which is capital D plus small d, will be the other root. It will be 240 plus 60 root 15. But you can also understand that we actually don't even need this. We can understand one thing, that small d will actually be how much? It will be, so it's like this now. If this distance is small d, oh sorry, if this distance is capital D, then on this side also, this distance will be capital D. from the symmetry. So small d is actually r minus 2 times capital D. Okay, so that's another way to calculate this. So you will see it will come out to be the same thing. Now root 15 we can calculate this way. Root of 16 minus 1. So 16 minus 1 to the power half. So take 4 outside. So 1 minus 1 by 16 to the power half. So that's approximately 4 into 1 minus 1 by 32. That's 4 minus 1 by 8. So that is 4 minus 0.125. So the approximate value is like this 3.87. So 60 into, so root 15 I will approximate as this.
So it should be 16 minus 10 in the under root.
Yes, so because sir, you only took out the 100, there's 4 into 360.
Oh, is it? Okay, okay. This is, no. Actually, it's 360 into 4, no?
Yes.
Correct. So it is 12 into 12 into 10, right?
Yes.
Yeah, 1440. So it's root 6 there. Huh? Okay. So this here should be 10. Then this calculation is not required. And this one becomes so this becomes 60 root 6. So this also will do an approximate calculation. So root 6 we can write similarly. Probably easy way of writing it will be 9 minus 3 to the power half. So that is 3 minus 1 by 3 to the power half. So that is approximately 3 into 1 minus 1 by 6. It's a very sort of approximate calculation because you can see that 22.5 squares is 6.25, whereas it should be 6, but we can write it approximately like this. Okay. So if you take it as 2.5 or maybe even 2.4, let's see. More accurate thing will probably be 2.4. No, it's something in between 2.47 or something like that. Okay.
It comes out to 2.44, sir.
2.44 is it? Okay. Yeah. I think it is 2.45 actually. Anyway, so 2.45 if you take, or even if you approximate it to first place of decimal, so it will come to this thing. It will come to 2.5. So anyhow, so this will become 240 minus 147. So this will be 93 meters approximately. So D will come out to be approximately 93 meters. And therefore small d will come out to be from here 480 minus 2 into 93, or same thing, 240 plus 60 root 3. So it will come out to be approximately 294 meters.
So could you please scroll up a little bit?
Yeah. Okay, so this is clear, people?
Yes, sir.
Okay. Now we will come back to more examples of numerical examples of using equation of trajectory and all. But with this, you will get an idea of how we are using. Now we'll look at next thing. We'll look at some variations of the standard projectile motion and how to deal with equations based on that. So next thing we'll look at is projection from a heighted point, okay, or projectile motion with projection, that is you're throwing the object from a height. So let's say geometrically our situation is now like this. We have this situation. That this is, let's say, our horizontal floor level, but this is a heighted point at a height h above it. And from this corner point, we can project an object. Now, the first case we look at is horizontal projection. If we project an object horizontally from here, then interestingly, even this will have a parabolic path, but it is like, one part of that parabola that we had seen earlier of ascent and descent. This is only going to be descent because we are projecting it horizontally. So from the word go, when we project it at t equal to 0, it's going to start descending because of gravity. It's not going to ascend because it does not have any vertical component of velocity, as you can see. So straight away, gravity will cause its y coordinate to start dropping from the projection point. And therefore, when it hits the ground, have some velocity v like this at some angle theta to the horizontal, let's say. The time will be some capital T, and this will be capital R, let's say in this case. Okay. Though here capital R should not be confused with horizontal range in a standard projectile, because this is not a standard projectile anymore. Okay. So given H and U and G, of course, the acceleration due to gravity's value, we should be able to calculate all these things. So calculate, first of all, we can calculate at any arbitrary time the velocity and the displacement and all that. Instantaneous values of these.
So where is theta?
It's horizontal enough. It has, so theta is with respect to horizontal is 0. You can see here this
No,
theta is
yes.
with the horizontal part. That, okay, that is the impact speed's angle with the horizontal that we want to calculate. Okay. Then we can find the distance at which it hits on the ground. We can find the impact speed, the angle of impact, all these things, the time at which it collides around all this. Okay. So again, what we will do is we will use the standard method of component based solving, vertical component and horizontal component. And here for convenience, what we can do is we can take the y-axis downwards because it's straight away going down. So no need to take the y-axis upwards. In a standard projectile, it was first ascending. So it made sense to take y-axis upwards. But in this case, straight away from t equal to 0, it starts descending. So the convenient choice of axis we can take is like this. We can take the point of projection again as our origin. It generally helps to do that. The direction of the horizontal velocity as our x-axis, and the direction of gravity now as our y-axis. So it
So
started
then the vertical component is only gt with the varies with time.
yes, the vertical, yes, correct. Okay. So what will happen is that at t equal to 0, it's at the origin. So x coordinate is 0, y coordinate is 0, ux is u, and uy is 0 this time. Okay. And the uniform acceleration is minus g, sorry, is gj cap in this case because I've taken. Okay. So gj cap. So acceleration's x component as usual is 0, but this time the y component will be plus g. So therefore, at any time t, you can see that the horizontal component of velocity will remain constant. The vertical component of velocity will become gt, and therefore the horizontal component of displacement will become ut, and the vertical component of displacement will be half gt square. So at time t, the velocity you can see will be ui cap plus gtj cap. But of course, remember this time my y-axis is downwards, and the displacement from the starting position will be uti cap
Sir,
plus, yes,
I didn't understand why the x component of u is sorry, the y component is 0.
because how we have projected, beta. This is the case where we have projected horizontally, na? So the initial velocity does not have a vertical component, na, beta.
Sir,
This is the
but
case.
we've just thrown it downwards at an angle.
No, beta. We have not thrown it downwards at a horizontal. Imagine you are standing on a balcony or something, and you've thrown something horizontally. You've not thrown it downwards. You're getting my point, na? This is horizontal projection. If we had thrown downwards, then there would have been some angle, non-zero angle with the horizontal, na? You understanding the point?
Yes, sir.
Okay. Or imagine you have a cannon from which you are firing a cannonball from a heighted position. Now, when you're firing the cannonball, the muzzle of the cannon, you have placed that muzzle horizontally like this from that point. So the cannonball, as it's coming out, is coming out with the horizontal velocity. Just at that moment when it comes out, it has a horizontal velocity. Then, of course, gravity starts acting on it. So the direction of velocity starts changing like this. Got the point? No?
So this is at t equals to 0, right? The case?
Yeah. This.
Okay.
I mean, projection. No? So projection is when the motion starts. So typically we start our stop clock at that point of time. Okay, so we'll take that as our t equal to. So the initial velocity, horizontal projection means that the initial velocity or the projection velocity u just has a horizontal component. It does not have a vertical component. So that's why uy is 0. Okay, so this is clear now?
Yes, sir.
Okay. Now let's do the second part of this, that is the impact velocity, time and all this with a numerical example of the same. So in the above situation only, suppose, so you got these equations. Okay. Now in this above situation only, suppose if the height from which we have thrown it is, let's say, 20 meters, and we take the value of g as 10 meters per second square, then find the time at which it hits the ground, the impact speed with which it hits the ground, the horizontal distance at which it hits the ground, and also the angle of impact. Angle of impact means the angle that the impact velocity makes with the horizontal. So Abhinav, see, that is a point. Na? U cos theta t, that is the standard formula that we've written for this standard projection, which is from the ground level at theta to the horizontal. But here we are projecting it from a height and such that that theta is 0. Getting my point? We are projecting it horizontally, no?
Yes.
So u cos theta just becomes u, and that's why uy, which is u sin theta, becomes 0.
Yes.
So it's the special case of that. Okay, so just note this method down for the instantaneous velocity and displacement, and then see how you will use these equations only. Okay, so the equations can be written like this over here, like I've done above, in component form. This and this are again, this is velocity in component form, and this is displacement in component form. So these are the same thing basically. Above they are written in component form, below they are written in unit vector notation. Now the main thing is you have to use these equations with these values to find out these things. Yes.
Sir, can we solve this sum in reverse? Like instead of, so we'll just change the signs of the values, and can we assume it that it's thrown upwards from that theta from the bottom,
It's
and
like
we'll just
half the
change the
projectile.
sign.
It's like half the projectile.
Right.
Yes, you can do it by that sort of method also. Okay. You can think of it like, you had projected it from somewhere before on the same horizontal level, and when it reaches the highest point, that is the snapshot picture, or that is the image that you're seeing at the projection actually at this point of time, at that heighted position. So in that case, capital H would have been your maximum height, and your horizontal range would have been double of the R that I've shown over here.
Yes, sir.
Okay. Yeah, you can do it by relating it that way also.
So, the angle at which something is thrown upwards at is the same angle it falls at, right?
Yes. Then what would have been your projection point before this maximum height position? That would have been symmetrical to your impact point.
Yes, sir.
So what is the initial speed, sir?
Yes, beta. Somebody had a question.
So what is the initial speed?
Initial speed is oh, right. That also has to be given. No? Yeah. So initial speed is let us say 15 meters per second. 1 5. Okay, very good, Aryan. Your answers are correct. Okay. Anirudh, your answer is also correct. Just check the value of theta in that. Okay. So what I think you should be getting here is that the time should be coming out to be 2 seconds. Okay. Which means that this horizontal distance will become 30 meters. Okay. And the impact speed will in fact become 25 meters per second. And the angle of impact will therefore become 53 degrees. So basically at the time when it impacts the ground below, you just substitute
So the final velocity is, I think, 20.
that's the vertical component. Horizontal component will also be there, no?
Yes.
What? No, so that's how it's 25. No, 59 cap plus 20 j cap.
Yes, sir.
Okay. Right. So I will just illustrate the calculation. Okay. So the important thing is, as you can see from this diagram, at t equal to capital T, the y component of displacement has become what the value of h is, or 20 meters. So start with actually this equation. Okay. So y is equal to half gt square. In that you substitute 20 meters at this time. So that gives you a first priority thing, that the time is 2 seconds. Once you got that, therefore you can see that the y component of velocity for impact velocity, it is 10 into 2 or 20 meters per second at impact. Okay. So from that we know now that the impact velocity as a vector quantity is 15 I cap plus 20 G cap. Okay. And also at the same time, the x coordinate is nothing but r. So u into t is, sorry, u into capital T in this case is equal to r. You substitute the value of capital T as 2 seconds. So 15 meters per second. So you're getting the r as 30 meters. Okay. So now you got everything. Now just you have to convert this vector into magnitude, which you can show is very easily 25 meters per second. And that angle. Okay, so this is your x-axis, this is your y-axis. Now you want to find the impact velocity's angle with this. Okay, this. So you can see it is tan inverse of the y component, which was 20 divided by this. So that comes out to 50. Okay. So you can say there's a bit of vector algebra involved, but it's actually really very simple. It is just about components and resolution of vector into components and nothing more than that really. Okay, so now we'll just take a look at another case of projectile motion from a heighted position.
Sir, 1 second.
Yeah. Okay, done.
Yes, sir.
Okay. And we look at the second case, oblique projection from that heighted point. So this time oblique projection can be such that you are giving it a initial vertical component which is positive, or you could even be throwing it downward sort of at an angle so that it has a vertical component that is actually vertically downwards. Both situations are possible, but both will be solved by more or less the same method. Just your choice of y-axis might differ a little bit. So I'll start with the example where it is like this. Suppose u is, let us say, 50 meters per second at an angle of 37 degrees. Okay. And this height is 35 meters. So when it hits the ground, Again, we want to find the impact speed, the time, this horizontal distance, and this impact angle. So here, because it is having a projection such that it ascends before descending, we can take the y-axis. So you can see that u is u cos theta I cap plus u sin theta j cap. So that is, see, for the given values, it's 40 I cap plus 30 j cap. So x component of initial velocity is 40, y component is plus 30, okay, and g is downwards. So you can see that the acceleration due to gravity is minus 10 j cap. So ax is 0, ay is minus 10 in this case. Okay. Minus because I've taken y-axis upwards. So from this you can see that at any time t, the x component of velocity will remain constant and it will remain equal to 40 meters per second. Whereas the y component of velocity utilizes such that it first decreases to 0, then it starts becoming negative. The x coordinate therefore is 40t. The y coordinate is ut minus half gt square. So this is the y coordinate, not vy. Okay. So now you can use this fundamental set of equations for solving for time, impact, speed, range, impact angle, all these things you can find out. So just give this a quick try. I'll give you the answers in a couple of minutes because we're almost out of time. I mean, we are out of time, but just finish this in a couple of minutes. Okay, so let's quickly finish this. Anybody's got the answers, you can send me. So you can see that at t equal to capital T, what should be the y coordinate? It should be minus h. Okay, so it should be minus 35 meters. So from this equation here, we have minus 35 is equal to 30t minus 5t square. So we can write that as t square minus 6t minus 7 is equal to 0. So see that is t minus 7 into t plus 1 is equal to 0, right? So t is either 7 seconds is the correct answer, or t would be minus 1 seconds. It would not make sense, negative time. Okay. So once you got that, so time is 7 seconds. So from that we can see that Vy would be equal to
root of
30, 10 into 7, it would be minus 40. Yes. Okay. So V impact would be 40 I cap minus 40 j cap. So the impact speed would be 40 root 2 meters per second, or approximately 40 into 1.4. And the angle of impact, therefore, you can see will become 45 degrees, because these are both 40 and 40, so it's very easy to work out. And the range would be ux into t. So r would be 40 multiplied with 7. So that distance at which it lands will be 280 meters. Okay. So it's really about, once again, using the fundamental equations of position, that is x and y, as a function of time, and velocity, that is vx and vy, as functions of time. In component form, you use it and just substitute the correct conditions. So no need to memorize any special formula and all this. Just basically get comfortable with how to use the fundamental equations in different conditions, whether we project horizontally or we project obliquely from the heighted position. Just remember this. Okay. So we'll conclude today's session here. Yeah, Sanvi, you have some question, madam?
So I got confused. Why did you take y as minus 35? Because t will be 0 at that point, right?
No, beta. See, t0 pe, what is the y coordinate? It is equal to 0, because I've taken the origin at the point of projection. And I've taken the y-axis upwards. So now compare the projection point, which is my origin, with this point where it's hitting the ground below P. You can see that it's 35 meters below. Understood? With respect to this reference frame, this x and y axis, what is the y coordinate of this point P? It is minus h.
So we won't take the maximum height.
Maximum height, though, we didn't need here, because it was not asked. But you can calculate the maximum height separately if you want.
Oh, okay, okay, sir.
Got my point? No? That's
Yes,
a different
sir.
thing compared to what is asked over here. Okay. All right, people. So we'll conclude here today. Now, there are lots of problems in HC Verma to do with projectile motion. I will send you a list of the questions to do. And of course, a lot of questions before that in one-dimensional motion. And in between, there are some questions in relative motion. So next lecture, we will start our discussion of relative motion also, after a few more things related to projectile motion and 2D motion in general. So I'll send you a specific list of questions to do from HC Verma and also from the module. And eventually I'll also send a sort of revision set of problems once you've completed these two things to solve from all these things. Okay. So just continue in the meantime with the questions in your module as well as HC Verma. That's it for today, people. Thanks for attending. Wish you all the best.
Bye, sir. Thank you, sir.
Thank you, sir.
Yes,
Bye.
sir.
Bye.
Sir, can you
Bye,
please send
sir.
the
Thank you, sir.
recording right now?